So let's continue with lecture 4. And one thing I forgot to do in the previous lecture is once I developed the flow sheet, I forgot to save the file, which is a big mistake. So the first thing that you need to do is like, so once you added your fluid components and once you created your stream, you can call it like input stream. The first thing you should do is go to file and then press save or save as. I'm going to save this one as say student version 1, and then we can put VCM. So you have to save, yeah. So also once we like after, how do you say, like so if you did something and then if you think everything goes well, you must immediately press the save button. Yeah, this is really important. So let's do that. So since I didn't save the previous file, I am going to repeat. I will do it very quickly. So what I'm going to do is I'm going to make the process flow sheet for the direct chlorination process. So I will just split the ethylene stream. You have to, if you don't understand what's happening, you should watch lecture 3. So I'm just splitting the ethylene stream into 2. So let's put 1, and then we can add one more stream, 2, and then it says unknown splits, that's normal. Let's put 0.5, so 50-50. Yeah, so we have a 757, so it will be exactly splitted into half. I think it should be 350 plus 350, 700. So 350 goes in 1 and 350 goes in 2. And then for chlorine, we supply slightly in excess to that of stoichiometric amount. On hydrochloric acid, we supply slightly in excess to that of stoichiometric amount. So if you remember the PowerPoint, so let's put the flow rate for chlorine, hydrochloric acid, 756 kilomoles per hour. Flow rate is 757 kilomoles per hour. So you should watch lecture 1, 2, and 3. Yeah? So this will be your lecture 4, whatever I'm going to record now. So we already splitted these two, and now we are ready to to mix chlorine and ethylene for the direct chlorination reaction. So let's mix. So it should be, we are going to mix chlorine and then ethylene from stream 1. So now it says required product stream, so let's put product stream as 3. All we are doing is we are just labeling the items. And then it says perfectly okay, so close this one. And then for the direct chlorination reaction, if you go back to our PowerPoint, we have to maintain 60 degrees centigrade, 1.5 atmosphere. Our stream 3, it's already at 1.5 atmosphere or 152 kilopascals. So all we need is to raise the temperature. So let's add a heater. So I'm going to, so the inlet will be 3 and outlet, let's call it as 4. And for energy, you can just give some label QE1. So everything looks fine. It says unknown delta P, that's okay. So you have to check the product stream 4. And another thing you have to notice, if you carefully look at the screen, you have something like a dark blue arrows, and here you see some sky blue arrows. If it's sky blue, which means some information is missing. So once everything is correct, this color will change to blue. So whenever you see some blue arrows, which means something is not correct and it needs our attention and we need to fix it. So double click on this. Let's say so temperature we need at 60 degree, and the pressure, there is no pressure change, so it should be at same 1.5 atmosphere. So everything becomes green, which means it's perfect, and you also see the color change. So it turned from sky blue to dark blue, which means this stream contains all the required information. Yeah? So this is perfect. Then the next thing is we're going to perform the direct chlorination reaction. As I said in the previous lecture, we are going to add CSTR. In the real industries, they will use a gas liquid contactor. Here we are going to use a simple continuous stirred tank reactor. So let's add it. So the stream, input stream will be 4. Output stream, vapor outlet, let's call it as vent. So we are dealing with the ethylene, which is a hydrocarbon. So probably some unreacted hydrocarbon should go out, and if there is any vapor, then it should come through the gas side. So, and also liquid outlet. So this is our product. So let's say 5. Everything looks fine. And if you look at here, so this is something that you should notice in the something that not notice it. You can even say it like some small advantage with Aspen HYSYS. So if some information is missing, it will tell you, oh, look at here, records a reaction set. So automatically you can think, okay, the next thing I have to do is I need to add a reaction set. So you have to go to this reactions tab, click the reaction set, press set 1, and then we have reaction 1. So this is stoichiometric reaction. I hope you all remember from the previous lecture. And then since it says volume not specified, okay, so go to design, click parameters. So we can specify 3000 cubic meter for the beginning. Let's assume liquid volume as 100. So everything looks fine to me, and everything turned green as well. So let's close this. And then I said to you, from the literature, we know that we need to maintain a residence time of 2.5814 hours in order to ensure complete conversion of the reactants to product. Okay, that's what literature says. Yeah? So if the rate of the reaction follows some particular expression which is given here, these values, then the residence time should be equal to 2.5814 hours for the conversion of ethylene into products. So let's do that. So how to do that? We need to add a spreadsheet like Microsoft Excel. We have to generate some formula, and then we have to optimize some values in order to make the residence time equal to 2.5814. And the formula is very simple. So I can show you quickly. Maybe I can draw in the same page here. So let's put it in the preview mode. So let's say you have some reactor of volume V and say some flow rate, meter cube per hour, and volume is expressed in meter cube. Then the residence time, we can use the symbol tau. That should be equal to volume divided by flow rate. If we meter cube divided by meter cube per hour, so meter cube will get cancelled. So the time will be equal to hours. So what we did is like we fixed the volume 3000 meter cube temporarily, and we know the flow rate. Flow rate is fixed, so we get 350 kilomole per hour, and then some additional amount, 364, or I don't remember exactly, kilomole per hour of chlorine. So it will be the total, the flow rate. So flow rate is fixed, and we need the residence time should be equal to 2.8514 hour. So for a fixed, if the flow rate is fixed and tau is fixed, so in order to get this fixed tau value equal to 2.5814, obviously we need to change the volume. So if we change the volume, so tau is equal to V by, let's go back to the Excel sheet. So if we double click the stream 4, the volume molar flow rate is 714 kilomoles per hour. So let's go back to PowerPoint. What happened? Something is disappearing. Okay, let's put preview. So tau is equal to, so V is equal to 7 by flow rate, F is equal to 714 kilomoles per hour. Sorry, I got a call. So coming back to this same problem, tau is equal to V by F. So what we need to do is like we need to fix the time or optimize the time so that it should be equal to 2.8514 hours, and our volume flow rate is fixed. So what we need to change is we need to change the volume. So what should be the corresponding volume that will ensure that our flow rate is fixed at 714 kilomoles per hour and our residence time will be exactly equal to 2.8514 hours. So this is what we are going to do at the moment. So how to do it? So it's simple. So go back to your Aspen HYSYS. So just I will show this quickly because I already showed it in the previous lecture. So all you need is to go to the palette, select the spreadsheet, drop it under near to your CSTR, just double click, go to spreadsheet. So you can give some name, say like a CSTR, and then maybe we can even say like say optimization of residence time. This is something like a title for the worksheet, and then let's put volume or maybe flow rate first. Flow rate, that's in. That goes to CSTR, and then volume of CSTR, and then residence time. Residence time. So in the flow rate, in the B column, B2 column, just right click with your mouse and then press add import variables, and then it should be the number 4 is the stream that enters the CSTR. So select stream 4, and then we have to select let's say the molar flow rate or total flow rate. It should be actual volume flow. I think that's correct. Let me check one time to avoid mistakes. It should be actual volume flow. So press done, and then our volume should be right click, add import variables, click CSTR unit, and then you have to select volume. It should be somewhere IJKL. It's in alphabetical order, so I just press tank volume. So select, press done, that's it. And then residence time is just a ratio of volume divided by flow rate in, so that should be equal to B3 by B2. So by default at the moment the residence time is equal to 0.2330, so 3000 divided by the flow rate in, that's equal to 0.2330. So we need to convert this into so we need to fix this value. So we need to perform some iterative calculations so that at the end of the day your volume will be adjusted in a way so that your residence time will be exactly equal to 2.8514 hours. So let's do that. So close this one, and to adjust this the residence time, you have to click the adjust tool. If you go to the model palette, follow my cursor, and then click this adjust, you will see something like a spanner plus or minus symbol. So select that one and then place adjust somewhere next to spreadsheet. Double click on the adjust value. So we need to set some objective. So select variable which we need to. So our objective is to change the volume. So it's volume CSTR tank volume, select, and then our target variable will be in the spreadsheet. that's our B4. So we need to change the residence time to 2.814. So spreadsheet, the variable should be B4, and that B4 should be equal to 2.8514 hours. So it will automatically adjust. The adjusted variable in this case will be tank volume. So it will adjust the tank volume so that your target value will be equal to 2.8514. Just press the start. Okay, 10 more iteration. Just say yes, 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 until you see until your problem is solved. So do you wish to continue? Yes, yes. Should have some patience. It may take some time. I think it's already optimized, so this is perfect. And now if you click the spreadsheet, you will see the new volume, 3.67 e to the power of 4 cubic meters. So that's the new volume. Yeah. So I think now everything looks fine to me. The flow rate is perfect. Vent looks fine. Composition. There is something with this with the rate expression that we took from the literature. Yeah. So 0.4902, 0.1186. So if you look at here, or if you listen to our lecture 2, what I said is like we're performing this direct chlorination reaction at a temperature. I can double click on the stream 4, temperature of 60 degrees centigrade and 1.5 atmosphere. And if you go back to our PowerPoint, first slide, so that's the condition, low temperature chlorination conditions, and then we took this particular paper and we followed some rate constants given in this particular manuscript, and we believe that this is going to solve our problem. But what I see from the results, so if the story that they say, or if the fluid properties is says like your ethylene dichloride should be liquid at this particular temperature and pressure, 60 degree and 1.5. So you are expected to see, what I just did is I just double click stream 5 and then I go to composition, and this is our ethylene dichloride, which is here. And if you look here, we have 0% of ethylene dichloride. Yeah? So which means either the reaction kinetics or the rate expression that we used is not enough to accurately predict the expected result. In fact, I'm following some textbook. In that book, they just did this exercise is following this literature value. So, but anyway, I checked myself. I went to the original research article. Anyway, I copy pasted here for you. Yeah, like published by Orejas, and that's the rate expression. These are the values we exactly used, and for some reason it's not working. So what we are going to do is, so this is something you learned at the moment, how to add a CSTR tank, how to adjust the residence time, and so on. But since this is not working for us, what we are going to do is like, I'm going to delete the CSTR tank, and then I'm going to add something like a conversion reaction. Yeah? So let's do that. So I will close this, and then we will delete the CSTR tank. We will delete the CSTR tank, and then we will add a conversion reactor. So before that, let's see whether we can. So let's delete this CSTR tank. Sometime I take a pause, I stop recording the videos, and then I do some calculations just to make sure whatever I'm doing is correct. So I will edit this video. So whatever the video which you are listening, I did a bit of editing. Yeah? just to save your time. If not, you have to watch very long video, like 3 hours, 4 hours. So what I'm going to do is I'm going to add a conversion reaction, so that will make sure the product will be ethylene dichloride, and let's assume 99% of our reactants are converted into products. So how to do that? So before doing that, we need to add a conversion reaction. Yeah? So we already added, if you go back to the direct chlorine, the PowerPoint, we already added this particular stoichiometric reaction. Another one is oxy chlorination and pyrolysis. Yeah? So, but since this is not working for us, I'm going to add a conversion reaction. So just to have a look on the stoichiometry, 1 mole of ethylene, 1 mole of chlorine will be converted into 1 mole of ethylene dichloride. And let's assume 99% of our ethylene is converted into products. So if that's the case, let's minimize this. So now we have to add one more reaction. For that, you have to click back the, if you see here simulation in the left hand side, and above you will see some properties. So click the properties, and then you have to go back again to reactions. Click reactions. We already have one set. If we double click the set, we will have 3 reactions: kinetic, one heterogeneous catalytic, and again another first order kinetic reaction. Since reaction 1 is not working for us, let's close this window, click reactions, and then let's add a new set. So once you add a new set, you will get something like a not ready. That's okay. So click add to the fluid package. Add to the fluid package. It's the same fluid package we are going to use, Peng-Robinson equation of state, and add set to the fluid package, Peng-Robinson equation of state. And then let's add the conversion reaction. So how to add the conversion reaction? Click the add, and then click conversion, and then press add reaction. So we have one reaction here. So close this window. So double click on RxN 5. Add components. Reactants are chlorine and then ethylene. Product is ethylene dichloride. So this looks fine. Stoichiometric coefficient is the same. -1 mole of chlorine minus 1 mole of ethylene reacts to form product 1 mole of ethylene dichloride 1. So this is fine. And CO, this is the conversion. So let's assume 99.9% conversion or 99.5%. So which means, so if you start with so 99% of our ethylene will be converted into products. Base component will be ethylene. So 99% of ethylene will be converted into products. In this case, the product, according to this stoichiometric equation, is ethylene dichloride. So let's close this. So we added one more reaction 5 in set 2, and just to keep in mind, in set 2 we have two kinetic reaction and 1 heterogeneous catalytic reaction. In set 2 we have 1 conversion reaction. Yeah? So let's go back to simulation. So this is a nice exercise, like how to deal with the problems. Yeah? So if we know how to go to literature, take the kinetic expression, and then we entered into Aspen HYSYS, and then we tried to add those kinetic constants, and we checked whether we get the desired product in the product stream. Obviously no in the present case, so we switched back to other idea. So we deleted the continuous state tank reactor, and then we added a conversion reactor. So this will make our life a bit easy, because it ensures 99% of our reactants are converted into products. And obviously for this type of the assumption, we don't need to add any rate kinetic expression. Yeah. So for your project, especially for this particular module, you need to submit some project which for which you have to use Aspen HYSYS, and try to get the kinetic constants from the literature. And if something doesn't work, then use this type of conversion reactor. Yeah? So let's go to the model palette. You can press the reactor. So and then we can put the cursor on each of these icons and see where is your conversion reactor. So the third icon, click on that and then drop it here. So this is our conversion reactor. So double click on it. Our input stream will be 4, and then vapor outlet. Let's put gas, and then liquid outlet. Let's put EDC 1. So it refers to ethylene dichloride. Yeah. So let's keep it like that, and then everything looks fine to me. And it says records a reaction set. So go to reactions. This time reaction set. Select set 2. Set 2, and there is only one reaction, which is reaction 5. It already added the conversion reaction here. You can check the stoichiometry. Close this window, and everything turned green, which means all looks fine. And if you come down and if you double click on the EDC, you have some numbers here, and you can check the molar flow rate. Something is funny again. Go to composition. You have 0.9552. So you have clearly product in the bottom, and you have very little amount of chlorine, excess amount of chlorine. Let's close this. Molar flow rate 365, 365. The remaining should be here. If you want, we can even check the flow rate. Like just right click on the stream and then add a show table. So it will show you the details. The molar flow rate is 365 kilomoles per hour. And it says its temperature is everything fine. You can still double click and check composition. Nine five two two. So let's right click on this and then add a show table. Something is for some reason it's not updating here. So half the flow rate is here, 365.58. If you click the stream 4 show table, so you have 714.0 kilomoles per hour goes into stream 4. So exactly the other half should be down here. For some reason I couldn't see it. So conditions. This is something that I don't like with Aspen HYSYS. So we didn't develop this software, so we're just using it. This should be exactly the remaining half. According to law of conservation of mass, the mass cannot disappear just like that. So for some reason it's not updating. Let's put on hold and then press active again. Okay, let's continue with this. It's okay. So let's continue this. So let's assume we have ethylene dichloride in the bottom, because we should have, because we already gave the conversion, and I see ethylene dichloride in the liquid here, 0.9522. Yeah, I hope the temperature is correct. 60 degree 1.5 at this temp, and let's say temperature here. Temperature is 1384. Pressure is 152. Temperature is not correct here. Let's change design parameters. These are variables, notes, reactions. Let's change the temperature. The temperature should be 60 degrees centigrade. Something is not right clearly. Now let's delete this. Let's delete and redo it again. So this is something you may encounter similar problems. So it's okay to do it again. Let's do this. Conversion reaction. Let's write product vapor. Let's say EDC1. Stream 4. And then let's close this and then click EDC. Let's fix the temperature to 60 and then pressure to 1.5. Here same, vapor, temperature to 60, pressure to 1.5 kilopascal. Close this, add the reaction. Reaction set to error has calculated. Close this, not solved. Unknown compositions, okay. It's not allowing to do this. Let's delete. I'm going to take a break and then let's do this again. I think I figured it out. I took a pause and then I tried to solve it on my own. So I found what's the problem. So you add the conversion reactor. So this is good practice for me as well. Yeah. So let's add vapor to vapor and then let's call this EDC1 and then let's add the reaction set. Let's do this. Let's repeat what we did before. Reaction 5, blah blah blah. Everything looks fine, but the only thing is the temperature looks a bit weird. 1384. So we can add some energy stream to control the temperature. So double click on the conversion reactor. So go to design, press QE2, press enter. So now it says unknown duty. We know that now. So what we do is, so now we use some energy to maintain the temperature in the conversion reactor to 60 degree, and the pressure is already set to 1.5 atmosphere. So just click on one of the stream, double click, and now check the temperature to 60. This should solve the problem. Yes. So now everything looks fine, and we see the molar flow rate 364 here. The top we should have the same 360. Molar flow rate is very low because we have 100% conversion. So that's correct. So 1 mole of ethylene, that should give rise to 1 mole of ethylene dichloride. So this is perfect to me. So, and if you remember, at this particular temperature and pressure, the ethylene dichloride is below the boiling point, which means if you've managed to form ethylene dichloride at this temperature of 60 degree and pressure of 1.5 atmosphere, it should be a liquid, and that's why you see them in the bottom. It's 364.7 kilomole per hour, and this matches with our stoichiometric equation. If you go back to the PowerPoint, which is here, so 1 mole of ethylene, we get 1 mole of ethylene dichloride. So we have we started roughly with around 350 moles, and then we added slightly excess chlorine, and then we see if we started with 350 kilomoles per hour, we should roughly get 350 kilomoles per hour in the product side. So the mole balance there, so there will be this perfect how do you call, like a stoichiometric balance. So I think, to me, I'm okay with this. The results looks good so far. We entered stream 4. We have 714. That is like a half. How much? Let's go back here. Ethylene flow rate is 350 kilomoles per hour. So this is okay to me. So if you want, we can add like a show label. Just right click on the stream, we can add show table, and then we can just keep it for reference. What's the molar flow rate at the moment, and just to make sure your temperature is at 60 degree and your pressure is at 1.5 atmosphere, which is equal to 152 kilopascals. So this looks good. Let me quickly go to check to properties, set to reaction 5 with respect to base component. No. Okay, it looks fine to me. I don't see a problem. This is okay. 364.7. I expected 350 kilomoles per hour, or slightly lower than that. Okay, let's continue with this value. So we already have ethylene dichloride, and in the vapor we have a bit of check the composition, some trace quantities of ethylene dichloride. Okay, no, vapor phase is here. Some concept. We have mostly ethylene and unreacted chlorine, and this is something I don't expect to see in the product. Vapors of ethylene dichloride. Okay, it's some low amount. If we convert it into weight percentage, it will be lower, I think. So let's stick to this. Let's close this one, and then let's come back to the other part of the problem, which is go back to the PowerPoint. So let's continue with this oxy chlorination. Just remember that process condition: 225 degrees centigrade, 4 atmospheres, and 350 kilomoles per hour of ethylene, and then roughly 756 kilomole per hour of hydrochloric acid, and then we supply air in excess. We need only 0.5 mole of oxygen. Yeah. So let's go back to our process flow sheet. So let's click back. So we can do the second part of our reaction. So let's do the oxy chlorination process. So we will do the same mixing business. Let's mix all the reactants. So just put a mixture, double click on the mixture. So we now our reactants include oxygen, hydrochloric acid, and ethylene. So let's add ethylene first from stream 2, and then we need to supply oxygen. Let's supply oxygen from air. Air contains, if you click here, like 79% will be oxygen. Yeah? And then we have to add hydrochloric acid. We already set the flow rate here. Yeah? If you double click, we can even check this show table. That's the table of our air, and then we can show table. That's the table of our hydrochloric acid stream. You can get some numbers here. So molar flow rate is 757 kilomoles per hour. Air goes at a flow rate of 1000 kilomoles per hour. And number 2, this one, if we put the cursor on this, you can see 350 kilomoles per hour of ethylene. So what it says now, okay, we need an outlet, so let's put some number for that. We already used number 4, so let's put 5. That's it. Everything looks okay. Press OK and close this window. So you have stream 5. So this is we are performing this Oxy Chlorination reaction. So now we have to add our catalytic reactor. So we will use a plug flow reactor and assume there is some catalyst inside. So click on the reactors and then check plug flow reactor, select it. Oh sorry, before that we have to do one thing, I forgot. So double click on this stream. If you see the temperature is 25 degree and 152 kilopascal. So let's raise the temperature to, if you go back to, I forgot the temperature, 225 degrees centigrade for oxychlorination, and we need a pressure of 4 atmospheres. So let's raise the temperature to 225 degrees centigrade. So click all, select heater, add this heater here. Our inlet stream will be 5, outlet stream will be, let's say 6, and let's say QE3, capital QE3. Yes, so it says unknown delta P, so we need to, if you know the change in pressure, we can give, or we can just enter the pressure at the exit stream. So that will automatically calculate the difference between the pressure in stream 6 and stream 5. So the pressure will be equal to 4 atmosphere and temperature, let's put the same temperature. What's that? 25C. Enter. Oh sorry, I don't know what I did. I did a mistake. So delete it. Sorry. Let's put the temperature to 225 degrees centigrade and pressure to 1.5. And then we will add a compressor now. So the pressure is same. So 5 and 6. We have the same pressure of 25 and 25, but we raised the. We raised the temperature to 225 degrees centigrade, but we maintain the same pressure in stream 5 and 6, which means delta P will be equal to 0. So now we raise the pressure from atmospheric pressure to 4 atmosphere. So we need a compressor for that. So close this one and let's search for a compressor. It's here. So put the cursor on the model palette. It will tell where is compressor. Click the compressor, add here, place it here. Just double click, add the stream. Inlet is 6, outlet is 7, and then recursion energy stream. So this should be QE4. So it seems like to production of monomer, vinyl chloride monomer requires a lot of energy to maintain the temperature, to pump the fluid, to so on, and also to perform the reaction at some higher temperature. chlorination, oxy chlorination at 225 degrees centigrade, direct chlorination at 60 degrees centigrade. So these things it should come into your mind when you're going to manufacture vinyl chloride monomer. It says unknown duty. That's okay. Close it. So now click the stream 7 and then click the pressure. Let's put 4 atmosphere. Yeah, that's perfect. So your temperature is temperature is changing. Okay, let's add a heater next to this and then see how it goes. Let's add inlet is equal to 7. Let's put outlet is equal to 8. Okay, anyway, by this way, what we are doing now, we are also practicing like how to add the minor unit operations and the major unit operations and so on. Yeah? QE4, unknown delta P. Let's go to close this one. Let's go to click the exit stream. Let's put the pressure to be 4 atmosphere. 4 atmosphere and fix the temperature to 225 degrees centigrade. Yeah. Okay, so this is something that we need in order to perform the oxychlorination reaction. So close all these windows. So let's add the heterogeneous catalytic reactor. So that one we are going to use a plug flow reactor. Assume that it contains catalyst already loaded inside. So let's go to click all and then, or maybe click the reactor and then add plug flow reactor. Click the icon here, you will see plug flow reactor. Select it, drop it next to here. So double click on your plug flow reactor. Your inlet stream is naturally stream 8 and then outlet, let's call it as stream 9. And this looks okay to me. Close it. And double click the stream. So the temperature should be equal to 225. Pressure should be okay, close this. Energy optional, let's put QE6. So now we can control the temperature inside the reactor. So double click on the stream 9. So temperature is 225, pressure should be 4 atmosphere. 4 atmospheres. So if what I did is like if you don't have the energy stream, it will not allow us to control the temperature and the pressure in the PFR. So we have to add this energy stream. And now if we double click on the plug flow reactor, if you double click on the stream 9, it allows to change the temperature and pressure. So which means the stream 8 contains 225 and 4 atmosphere and stream 9 contains the same, is maintained at the same temperature and pressure, which means the reactor conditions should match with this whatever the condition that goes in and that comes out. Yeah, so just close this one. So to me everything looks okay. So you see this some red, bright red on the unit operation. It means something is not fine, something is not solved, and we have to do something to fix it. So if there is no mistake, all the unit operations will look like a green. Yeah. So just to double click on the plug flow reactor, it will give the information like what we need to do. Requires a reaction set. So we need to add the reactions. So we need to select set 1. Under set 1, some problem. Okay, so we selected set 1 and then go to the details. The reaction should be reaction 2. So this is the heterogeneous catalytic reaction. So click on that. Everything looks fine, and then it says unknown dimensions. Okay, so what we do is like let's begin with some number. So ethylene. So go to design, connection, parameters. Temperature, pressure, molar flow rate. I'm just checking where is the information to enter the volume. We have to enter the volume of the reactor. Connections is here, parameters. We have to mention the, okay, it's here in the rating. So let's assume the total volume may be, let's start with the 2000 cubic meters. We can change this later. Yeah, so we have to optimize the residence time in the plug flow reactor as well. So we have to think about this. So let me check the small sheet which we prepared. So let's assume diameter is equal to 11. So, but at the end of the day, we are going to change. So, what the literature says to us is like the residence time should be roughly around 0.09 hours, and then the length to diameter ratio should be equal to 1.50. So these are the industrial conditions. So this one we took from the literature. I forgot which paper. So this is from the work of Lakshmanan et al. So wait a second, let me check. It's from the same paper which is in our PowerPoint. It's from this work. If you see here, for Oxy Chlorination reaction, so roughly 324 seconds. Yeah, that's roughly 0.09 hours. So that's the amount we are going to fix it, 0.09 hours. Yeah. So that's the residence time. So let's go back to our plug flow reactor. Hope I'm not confusing you, because I'm getting confused myself. Aspen HYSYS is a very user-friendly software, but you should know the details before. So at the moment we just assume our reactor volume is 2000 cubic meter, which is more than enough to handle the flow rate which we are dealing with at the moment. And then the diameter we are going to fix it to 11 meter, and then later we have to fix the length to diameter ratio of 1.5. Okay, so we will adjust the length to diameter ratio, and then we will also adjust our residence time roughly equal to 0.09 hours. So it's very low, the residence time is extremely low, and there is a reason for that. So if you increase the residence time, obviously it's going to degrade our sample. Yeah, so probably you won't get our product at the end. So let's check that whether the literature value is correct or not. It should be correct. Whether it works in Aspen HYSYS or not, that's what we are going to check. So let's close this window. So what I did is we added a PFR unit, we added the energy stream, we changed the stream 9 temperature and pressure 225 and 4. So let's close this, and then so you can change the temperature and pressure in the product stream only if you have if you double click PFR, you must mention an energy stream QE6 in this case. Okay, so try to do this bit slowly, bit by bit. Obviously, if you have doubt, you can always ask me. So I will close this. Everything looks fine to me. So now we need to adjust the residence time, and then we also need to adjust the spreadsheet. Okay, so sorry, residence time, and we also need to adjust the length to diameter ratio, and for that we need to create a spreadsheet like what we did earlier for the continuous stirred tank reactor. So let's click all, select the spreadsheet, drop it under PFR. So double click on PFR, go to spreadsheet. So let's say PFR, say optimization of residence time. So this is the title, and then how to optimize this. So let's say flow in, and then volume. Same formula. So volume divided by flow rate, that should give the residence time. So let's call this as residence time. So what is this flow in? In this case, stream 8 goes into the plug flow reactor. So go to B2 cell, right click with your mouse, add import variables, and then you select stream 8, and then here you search for actual volume flow, which is here. Click it here. So this is your actual volume flow. This is done. Happy. And now for volume of plug flow, just right click, add import variables. We have to select plug flow reactor, the whole unit, which is PFR 100. Click on that, and then what we need to select, we have to select the tank volume. MNOPQRST. I couldn't see the tank volume. So this is the unit is PFR 100. Okay, add import variable. PFR, what to do? Okay, let's hear reactor volume. Click that one, add it. So we have reactor volume, so done. So now the residence time will be the ratio of these two. So that should be equal to B3 divided by B2. Okay, it's some small number. That's okay. And then we can create one more in the same flow sheets. Let's say length to or L by D ratio, L by D optimization, maybe let's call it like that. So now we can add say tube diameter, and then we can add a tube length. So let's put tube length in the top. So right click on this, add import variable, select PFR unit, and search for the tube length. So PFR unit, number of tubes. So I couldn't see the tube diameter. Tube diameter is okay, tube length is here. So add it, done. And then for tube diameter, just right click, add import variables, go to PFR unit, select tube diameter, click it, press done. So that's fine. And then now L by D ratio. So this should be equal, sorry, Oh, what happened? Okay, let's delete this. So here is length by diameter equal to B7 divided by B8. B7 divided by B8. This is same like entering the formula in Excel sheet. So at the moment the L by D ratio is 1.9. So we have to fix it to 1.5. So how to do? We have to change the residence time to 0.09 hours and then length to diameter ratio to 1.9. Okay, so let's do that. So let's first fix the residence time. How to do that? We need the adjust tool. So click adjust, place it somewhere here, and then double click on adjust. So what we need to change now? So we need to change the residence time. And if you go back to our PowerPoint, I showed you already here, maybe here. I said what's the relationship between the residence time to volume to and flow rate. So we are going to change the reactor volume, and then in order to optimize our residence time. Okay, so go back to our Aspen HYSYS. So select variable, go to PFR and select the volume, reactor volume. Select. So we are going to we are going to adjust the value of the reactor volume. That's why it says adjusted variable. And then by changing what? Select variable, the target value. The target will be the residence time. Yeah? So we need to, that's our target variable. So where is that? You have to select a spreadsheet. Not spreadsheet 1. What is this? Okay, this is spreadsheet 1. And then we have to select B4. B4 is the residence time. So select. Let's select it. And then our objective target value is 0.09 hours. So unknown maximum. Okay, let's start. Okay, everything looks fine. So this our residence time is 0.09 hours. Close this one. Let's click there. Now you see here residence time 0.09 hours. So now we have to change the length to diameter ratio. The procedure is exactly the same. So let's close this one. So we are going to change the tube diameter so that at the end of the day the length to diameter will be equal to 1.5. So close this one. Or you can even change the length in order to make sure the length to diameter ratio is equal to 1.5. So for the moment, let's change the tube diameter so that at the end of the day our length to diameter ratio will be equal to 1.5. So how to do that? We have to select one more icon. You have to use the adjust tool or function again. So click adjust, drop it again here, double click on it. So this time our adjusted variable. So we have to adjust, say, the diameter of the plug flow reactor. So go select the PFR unit, select the tube diameter somewhere here, select, and then now our target is to change the length to diameter ratio. So select. It's in our spreadsheet. We already calculated it. Spreadsheet B9. So that's the ratio of B7 by B8. Select. And we are going to fix this value to 1.5 and then press start. We solved it. So we used two adjust functions so that now what we have is we have a PFR unit whose length to diameter ratio is fixed to 1.5 and also the residence time is fixed to 0.09 hours. So I hope you all follow up to this point. So this is a very good example because it gave us a chance to learn how to adjust the residence time, how to use these tools like spreadsheet, adjust tool, which are available in Aspen HYSYS in order to optimize something specific in the design calculation. Yeah. and we also know how to add like like this major unit operation and minor unit operations and so on. And we also learned like at, like how to adjust the temperature and pressure. So if the pressure in the stream that goes in and the pressure of the stream that comes out are same, which means the delta P is going to be 0. So we learned a bit in this process, and then we also learned how to add reactions in a set, and then we also created a new set where we added a new reaction, conversion reaction, and then we know how to add a CSTR, we know how to optimize the residence time in the CSTR, and then we realized that the the literature value didn't help us, so we deleted the CSTR and then we replaced it with a conversion reactor and so on. So these are the things you should keep it in the mind. So I think you might have learned already a lot in Aspen HYSYS, some of the features available in the HYSYS. Soon we will learn liquid extraction, absorption, distillation, especially the distillation part. I think Aspen HYSYS will be like a god for us. It's going to help us to find a lot of parameters required for the design of a distillation column. So you are going to appreciate it once you finished learning the techniques available within the HYSYS. So let's go on. So we are happy with this thing so far. So just click on the stream 9. So we don't have to blindly believe like a fool, like literature says 0.09 hours something is going to get converted into product. Let's check whether it's a true or not. So let's see, is there anything in the product stream? Ethylene dichloride. Yes, of course we have product in the final stream. So we have some amount of ethylene dichloride in the liquid phase and also in the vapor phase. That's good news. So let's stick to that. So which means we are happy with it. So we can move this slightly right side. So what we are going to do now is we are going to mix both this ethylene dichloride from the direct chlorination reaction and the ethylene dichloride from the plug flow reactor, from the Oxy Chlorination reaction, and then we are going to mix both of them, and then we are going to purify the product stream, and then finally we will use the purified ethylene dichloride to manufacture vinyl chloride monomer. So and then we have to mix these things. Let's mix it. So let's mix. Maybe we can also mix the products from the vapor phase and also from the ethylene dichloride. So or maybe just take this ethylene dichloride because we already assumed 99.9% of purity. So let's take this ethylene dichloride. Let's add a mixing unit. So double click on this. Let's take ethylene dichloride from the direct chlorination step, and then we can even change this stream 9 to EDC2, ethylene dichloride 2. So click on the 9 and then just to type EDC2. So to change the name of the stream, you need to double click on the stream, and then you see the stream name, just to double click there, and then you can just type directly EDC2. So it will change the name. So we will, in the mixture, we will connect EDC1 and EDC2. So we are okay with this. And then we need a outlet stream. So let's call it as we have 6, 7, 8. Let's call it as stream 9. Okay, it looks good to me. So the final temperature of this stream conditions, temperature is at 60 degree and 4 degrees. 225 and 4. Let me check the pressure and temperature of these units. So let's check the composition of stream 9, what it contains. So it contains water, not a good news. It contains air compounds, oxygen and nitrogen. It contains our main product, ethylene dichloride, trace amount of ethylene, and some amount of chlorine and hydrochloric acid. So we need to purify them. So we need to get 99.5% pure ethylene dichloride in order to avoid cooking in the pyrolysis chamber. Yeah? And also remember, like water will form azeotrope with hydrocarbons like ethylene, and so which means it will become very difficult to separate. So as I said in the lecture 2, what we are going to do is, so we are going to use, let me check my notes. So we are going to use a liquid extractor using water as extractor to purify ethylene dichloride. Yeah? So we will get a pure ethylene dichloride and everything else will be mixed with water. So we will take the water out and then we will get the pure ethylene dichloride as the product that we need. So what we do for that? So before that we will separate. We will separate. Let me check. So we already have water and other things. I need to check my notes for a second. I hope you already have those key sheets which I asked you to write. So what we are going to do is we are going to add a small flash column, and we are going to maintain the flash column temperature to 15 degree centigrade. So at this 15 degree centigrade, your water and all the liquid products, which like ethylene dichloride, they are going to remain in the liquid phase. But at 15 degrees centigrade, your air components and also hydrocarbon, this tiny gas which you see here in the vapor phase, they will disappear in the vapor stream. So that will give some level of purity. At least we will remove the air components and then we will remove this ethylene. So let's add a small flash evaporator and then like a flash column, and then it will separate these components, hydrocarbons and some of the air products. So let's do that. I will close this one, and then so if you click on stream 9, at the moment the temperature is 60 degree and atmosphere is 60 degrees centigrade and pressure is 4 atmospheres. So we are going to maintain this at 15 degree centigrade. So let's change the temperature. Close this. So how to change the temperature to 15 degrees? So let's add a cooler. So this is the first time we are adding a cooler in the process flow sheet. So click on the cooler, drag and drop it here. So double click on cooler. So inlet stream is going to be stream 9, outlet stream is going to be stream 10, and QE energy value, let's put QE I forgot which number we used, QE4, QE5, QE6. This is good. I think now it's fine. Why it still says records and energy stream? Okay, probably QE9 I used somewhere probably. Let's put QE10. Yes. And then let's put, if you want we can add the pressure in the right hand side, or we can add just delta P equal to 0. And then unknown duty, that's okay. Close this. And then click on stream 10. Let's fix the temperature to 15 degrees centigrade. Everything looks green. So it's time to add a flash separator. So normally flash column, they use it in the industries mainly to reduce the workload of the next unit operation that follows the streamline, the product line. So our process line, I don't know how to say it exactly. So you will have, say if you're having some distillation unit somewhere around here, in order to reduce the workload, or maybe like an absorption column, for example, to reduce the workload, normally we add a flash column to remove some of the lighter components from the heavier components. Yeah, so that's the main purpose of adding these flash columns. So if you go here, if you click on if you look in your palette, model palette, somewhere around you will see here separator. So click on the separator, add it, place it next to stream 10. So just to double click on this, I think this should be fine. So, and then your inlet is obviously stream 10. Vapor outlet, let's call it as I don't know what name to call. I'm already tired. Let's put lights, or maybe just put okay, I don't know. Yeah, lights, it refers to the hydrocarbons and air components. And then the liquid, let's put stream 11. You don't put any big name. Let's put stream 11. Just a double click. Everything looks okay to me. Close it. So click on the 11. Temperature is 15, pressure is 4. So let's see the lights. Composition. Vapor phase, we already have some ethylene, and then we have some air components. Let's check the purity here. Okay, I'm going to move it to the right side for convenience, and then just right click on stream 10, right click, show table, and then you just put your cursor on the table, just double click on the table, and then you will see something like add variables. Let's click add variable. Let's put molar flow rate, and then phase molar flow, and then let's see liquid phase. Molar flow rate, and put mole fraction, sorry, and then go to phase component mole fraction, master component mole fraction. Let's just click ethylene dichloride, which is here. Click on it. Done. So 0.3585. So put the table somewhere here, and then you do the same thing at stream 11. Just right click on stream 11, press show table, and then double click on the table, add variable, go to mole fraction, press master components, press ethylene dichloride, click on it, press done. Okay, this is not a good news. Molar flow rate is 0. Why is that? Okay, just double click on the add energy stream. Let's put Q11. Close this and then select the stream to temperature to 15 degree. And still the molar flow rate is not correct. Let me fix this. What's the problem? Something is not correct. It's we should get a massive flow rate in the liquid side. We will get ethylene dichloride plus water and so on. So let's check what's the flow rate in the top. Show table. Flow rate is 1947. Everything goes in the top. So nothing comes to the bottom. So we have the temperature to 15 degrees centigrade, 4 atmospheres. Okay, this is fine to me. What's the problem? Separators. So we have a lights QE1. There is no reaction for this. Parameters. User variable nodes. Stream 10. Something is not correct in this. Liquid outlet is 11. This cannot happen, yeah? Like water cannot go to the top. So I will pause the video, I will fix this and then I will continue recording. Let me figure it. I need some time to check what's happening. So I'm going to stop recording the video and then I will come back.